The recurrence we have to solve now is a 3 terms recurrence, but other than that it's just as simple as any other. And this is particularly simple because it's homogeneous, so the right hand side is 0. Don't have to worry about that, right? Of course, if it is a 3 terms recurrence, we need two starting values, so we need a0 and a1, right? The generating function we're going to use is standard, is the ordinary generating function of this sequence, right? As in any case. Okay, and the procedure is the same. We have to multiply by set to the highest exponent, the highest index as exponent. So you have set n plus 2 times a n plus 2 minus 3 set n plus 2 a n plus 1 plus 2 set n plus 2 a n, and that is equal to 0. All right. Now we have to add all the range of indices. So from n0 to infinity, set n plus 2 a n plus 2, right? Minus 3 sum from 0 to infinity, set n plus 2 a n plus 1, right? Plus 2 times the sum from 0 to infinity, set n plus 2 a n, right? That's equal to 0. Okay, now we're going to shift the index here, right? So we have the sum from 2 to infinity set to the n a n, right? We're increasing 2 units here, so decreasing 2 units here, so we have this here. Okay, now in this case, first there's a mismatch between the exponent and the index. This is n plus 2, this is n plus 1. So first we are going to get out a factor set, and second we're going to shift 1 unit the index here, right? So we have set to the n a n after doing that. And finally in this one, the only thing we have is a mismatch between exponent and index, so all we have to do is to take 2 factors set outside. So we got this set to the n a n, and that is equal to 0. All right. Now this one here is just the generating function. This one here is the generating function, but it's missing the first term, the n equal to 0, which is a0. So it's the generating function minus a0, which is 1, right? And this one here is again the generating function, but there are 2 terms missing. The term n equal to 0, which is minus a0, right? But then we also have to subtract the term n equal to 1, which is a1 times z. a1 is 6, so minus 6 z. Now we gather these 3 functions together, and then we have f minus 1 minus 6 z minus 3 z f plus 3 z plus 2 z squared fz equal to 0. All right. We can factor out the f, so we have 1 minus 3z plus 2z squared, right, times f. Okay. Second, we have minus 6z here plus 3z here, so that is minus 3z, and we put it to the right hand side, so we have 1 plus 3z, and from this we get that f is just 1 plus 3z over 1 minus z times 1, it's 1 minus 3z plus 2z squared. All right, so this is our function. Okay, now we need to factorize the denominator in order to proceed, right? And factoring the denominator, of course, you can find the roots of the polynomial here, and this is one way, but it's easy to spot that this denominator is just 1 minus z times 1 minus 2z. Okay, because you have 1 here, right? Minus z minus 2z is minus 3z, and then you have minus z times minus 2z, which is plus 2z squared, right? So This is the factorization, so what we have is 1 plus 3z over 1 minus z times 1 minus 2z. And this fraction can be factorized, well, can be split as the sum of two fractions, this and this. Okay, because we have two different factors and each one has multiplicity 1. So the expansion in elementary fractions is like this. So this is equal to, after multiplying by the denominator, this is 1 plus 3z is equal to a times 1 minus 2z plus b times 1 minus z. Now, as usual, we give values to z, so take z equal to 1, right? And if we do that, these terms cancels, so we have 4 here equal to, after making 1 here, this is negative 1, so this is minus a. So a is minus 4. And if we take z equal to 1/2, then this is the factor that cancels. So we have 1 plus 3/2, which is 5/2. That is equal to 1 minus 1/2 is 1/2, so b/2. And that is b equal to 5. All right. Okay, we already have the coefficients, so f is just, we have it here, it is 5 over 1 minus 2z minus 4 over 1 minus z, right? Now expanding this is very easy because both are the geometric series, right? So what we have is, in this case, 5 times the sum from 0 to infinity, 2 to the n, z to the n, and there you have minus 4 times the sum from 0 to infinity, z to the n. Therefore, the coefficient an is equal to 5 times 2 to the n minus 4 times 1, so 4, right? So this is the solution to our recurrence, okay?